Okay, MA1002, continuation of tutorial 4. We're going to jump in on question 2. We have a copper-silver alloy of composition 38% silver and the balance copper at 775 degrees centigrade. And you are asked to determine the mass fraction of both the alpha and beta phases. Now, first of all, we need to examine the phase diagram. We have temperature against composition. We have an alpha and a beta phase, which is actually a common way of labeling phase diagrams. So many binary and tertiary phase diagrams have both an alpha, beta, possibly a gamma. It's just a labeling system. So here we have liquid, here we have alpha, here we have beta. Now we can ask a number of questions from this phase diagram. At a particular composition and temperature, what phases are present? Well, here there is alpha, here there is alpha and beta, here there is beta and liquid, and here there is alpha and liquid. Now we notice first of all that this is a eutectic phase diagram. In fact, there is a eutectic here, and basically this is analogous to solidification. As we go from a high to a low temperature, we pass from a liquid to a solid phase. Now, the difference between normal solidification and a eutectic is that we have two different phases present. So we have alpha, which is essentially dominated by pure carbon with a small amount of silver. In this case, the maximum solubility of silver in copper is 8%. And the beta phase is actually very different from the alpha. It's pure silver or mainly silver with a small percentage of copper. So here you can work that out. It's about 8.8% copper. So the question deals with 38% silver, and let's just see what happens at this particular composition. At high temperature, we have a liquid. We cross this region here, and we start to have the development of a solid phase, solid and liquid in equilibrium, and we get to just above the eutectic, and we have both alpha and liquid. Now, the crucial point for this question is when we're just above the eutectic temperature, the composition of the liquid is determined by the intersection of the tie line with the liquidus line, and you can see that it actually becomes equal to the eutectic composition. So just above the eutectic we have alpha and liquid, with the liquid having the eutectic composition. As we cool to just below the eutectic, the alpha changes a small amount, but the liquid fully transforms to give the eutectic combination of alpha and beta. Now, the first part of the question, of course, deals with the total amount of alpha and the total amount of beta. And we don't really care where the alpha and beta come from, what part of the microconstituent. So what we do is we use we draw a tie line. The question is about alpha and beta, so the tie line is going to extend from the alpha to the beta boundary. And we can work out for example, the percentage of alpha will be 91.2 minus 30, so it's this line here, divided through by 91.2 minus 8, which is the full tie line length. Now, this vertical dimension is exaggerated, but really we're actually just concerned with below the eutectic isotherm. So ordinarily in solid state physics, when there is a liquid, there is a rapid change of composition. Here there is still a liquid, but when we get into the solid phase, we wouldn't expect significant changes as we go to lower and lower temperatures. So normally we do the measurements just below the eutectic or eutectoid isotherm. So the amount of alpha is 74, so the amount of beta would be 26. Fair enough. Now, the second part of the question is to determine the mass fractions of primary alpha and also the eutectic microconstituent. So this brings me back to my earlier point. If we consider just above the eutectic isotherm, then we can work out the percentage of alpha and liquid. Now, after cooling to just below the eutectic isotherm, this alpha then becomes primary alpha, and all of the liquid is in fact actually transformed to give the eutectic composition, which is a combination of alpha and beta. Why does that happen? Well, whenever the liquid has the eutectic composition, it will transform to give you the eutectic microstructure. So as we go from high to low temperature, the composition of the liquid is determined by this liquidus boundary, and you can see it asymptotically approaches the value of 71.98%. So my point is, if we can work out the percentage of alpha and liquid above the eutectic isotherm, this will in fact give us the percentage of primary alpha and also eutectic microconstituent just below the eutectic isotherm. So the percentage of alpha is going to be 71.9 minus 30 divided through by 71.9 minus 8, and is about 66%. So of course the percentage of liquid, if we could count, would be 34%. Now we know actually that the percentage of alpha is also equivalent to the percentage of primary alpha. So the percentage of primary alpha is the same as the percentage of alpha, more or less. And the percentage of liquid is in fact actually the same as the percentage of the eutectic microconstituent. So it becomes clear now that we have two things. First of all, we have an estimate of the total amount of primary alpha present. And that primary alpha, of course, we have an estimate of the total amount of alpha present. Now that alpha phase actually appears in the primary alpha and also as part of the eutectic microstructure. We also have an estimate of the percentage of primary alpha. So when we get to the third part of this question, determine the mass fraction of eutectic alpha, it should be just a question of doing a simple calculation. So total alpha is the sum of eutectic alpha and also the primary alpha. Do a little bit of mathematics and the percentage of eutectic alpha comes out about 8 weight% of silver. Okay, so again, to recap one more time, since we are actually to the left of the eutectic, then we're not dealing with entirely eutectic structure. There is a combination of the eutectic phase. Of course, the eutectic phase is alpha and beta and alpha and beta. And also we have a primary phase, in this case, alpha. If we were to the right of the eutectic, we would have the eutectic structure and also we would have primary beta. And if we are at the eutectic, it would just be entirely the eutectic microstructure. Question 3 is really a question of identifying microstructure or microconstituent and doing a little sketch indicating the compositions. So we have a more complex phase diagram now, still binary, copper, zinc. Melting point of pure copper is about up here, 1090 degrees centigrade about. Melting point of pure zinc is down here. Always can read that off. You notice the solubility of zinc in copper is very high. You can see all of this region here is the single alpha region. And actually, We have a number of features on here. We have some that we recognize. For example, this is an example of a eutectoid. A eutectoid is where upon cooling, one solid phase changes to two different solid phases. Here we have liquid, so above this temperature, for all compositions, it is liquid. So the phase which is present at 1000 degrees centigrade at this composition is liquid. So how do we draw liquid? Well, you know, use your imagination. You can draw some wavy signs inside there. The composition actually is the same as the composition of the question, 68 weight % zinc, because it's just single phase. Second temperature, 760 degrees centigrade. Well, that's clearly in the gamma and liquid phase region. So now our sketch becomes a little bit more complicated. We have a solid component and a liquid component, and we can estimate the composition of both gamma and liquid. So the gamma is approximately, we follow this tie line to this region here, we move down, 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 is approximately maybe 67 weight % zinc and the balance copper, whereas the liquid is approximately 78 weight % zinc and the balance copper. So my estimates are a little bit off. So we have solid inside here, we have liquid around the outside, in equilibrium. The next temperature, 600 degrees centigrade, we're in a single phase region, so we already know the composition. So you can just draw a solid. I've added some grain boundaries in here just to actually make it quite clear that it is a solid. And the final one, 400 degrees centigrade, is in the gamma and epsilon region. These are both solid phases. We know that because there isn't the symbol liquid. And again, by actually working out the intercept with the gamma boundary here, or the epsilon boundary here, we can estimate the compositions of these two components. So again, it's a solid. I put a grain boundary in there to depict it's a solid. And here we have the epsilon phase, and the background is the gamma phase. And you can see actually that the epsilon is determined by this portion here, which is around about 78 weight % zinc, 22 weight % copper. And the composition of the gamma is around about 67, 68 weight % zinc.